Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Engineering and Technology, SOET, Certificate in Smart City Development and Management, CSCDM. MIO 002 Smart Technologies, Hardware and Software. Block-1 IoT, IIOT and IOE. Unit-2 Industrial Internet of Things, IIoT, and Internet of Everything, IOE. 2.1 Introduction to IIoT. IIOT is the advanced form of IoT and it is used in industrial applications such as agriculture and manufacturing. The Industrial Internet of Things, IIoT, is the application of the Internet of Things, IoT, in an industrial setting which applies smart technology, smart sensors, data collection, storage, and cloud-based analytics connected together using the Internet's infrastructure to achieve value-added performance within an industry's enterprise. In the simplest of words, IIoT can tell an oil and gas company how to minimize impending damage and disruption before leakage occurs in a gas pipeline. Whereas in IoT, home users are informed when to feed their pets on time. IoT is the interconnection of smart devices that monitor, inform, and enhance personal aspects of everyday life via the Internet. IIoT, in a similar way, builds on the same technology and concepts as IoT to provide the ability to connect businesses, people, machines, data, and devices within an industrial setting, specifically targeted to enhance the performance across the manufacturing value chain. For example, the robotic arm on an assembly line, a thermostat in a freezer delivery truck, or a pump that provides fresh water are all connected, providing and sharing data to make informed real-time data-driven decisions that better control the process they are part of. IIoT technology can be applied to solve difficult logistic, manufacturing, and supply chain issues that benefit both the manufacturer and consumer. Leveraging IIoT in an existing enterprise is a mutually beneficial aspect of IIoT implementation and can reduce operational costs while ensuring the highest quality possible in a wide variety of an industry's processes. Objectives. After studying this unit, you should be able to define IIoT and IOE. Explain the differences between IoT, IIoT and IOE. Describe IIoT technologies and concepts. Discuss the pillars of IOE and know the Industry 4.0, Automation of Industry, 2.2 Definition of IIoT. Industrial Internet of Things, IIoT, is a subcategory of Internet of Things, IoT, that refers to the use of automated, interrelated sensors, devices, and machinery to drive operational efficiency at an industrial scale. Most IIoT definitions highlight that these systems are characterized by a connection between the cyber and the physical, or information technology, IT, and operational technology, OT. The IIoT consists of Internet-connected machinery and the advanced analytics platforms that process the data they produce. IIoT devices range from tiny environmental sensors to complex industrial robots. While the word industrial may call to mind warehouses, shipyards and factory floors, IIoT technologies hold a lot of promise for a diverse range of industries, including agriculture, healthcare, financial services, retail and advertising. 2.3 Why Industrial IoT? Speciality of IIoT. The Internet of Things, IoT, is all over the media with particular attention to the process and manufacturing industries for which the name Industrial Internet of Things, IIoT, is used. There are also IoT solutions for other application areas like transportation and healthcare etc., but we don't hear about IoT or IIoT. What makes industry so special that it has to be singled out as IIoT? IoT is about digitally networking things such as sensors and actuators from the very first meter and then securely all the way across the internet so all their data can be accessed from anywhere including the other side of the world. For the industry this means 4 to 20 milliamperes and on-off signals are no longer sufficient. You need digital networking all the way from the sensors and actuators, bus or wireless. It is when it comes to the sensor. The home and office environment are not demanding and the applications are not critical, so Ethernet, Wi-Fi, USB, and Bluetooth work fine. However, applications in plants boiling petrol, refinery, mixing volatile chemicals, and power generation, ensuring no blackout, are mission critical requiring real-time digital closed-loop control. The outdoor applications on the process itself have challenges such as hazardous areas, explosive atmosphere, rain and sea spray, dust, hot deserts and bitter cold winters. Direct sunlight, electrically noisy, switching and frequency control of heavy electrical loads, long distances with huge ground potential differences. There are other circumstances that make industrial applications challenging. For instance, the industrial sensors and actuators are handled by people with only big tools in their toolbox, and they must be able to replace these things without having to touch system software because their responsibility is instrumentation, so they are not allowed to work on the control system. The number of sensors in a plant outnumbers those in a home by several orders of magnitude. Clearly, more sensors and actuators are an industry trend as plants are becoming ever larger to get economy of scale, and the processes are more complex to handle lower grade feed and meet increasingly stringent requirements for a finished product. Plants are deploying more sensors for equipment condition monitoring to improve reliability and reduce maintenance cost, for performance monitoring and loss detection to improve energy efficiency, automate balance manual data collection for productivity, and to meet ever more demanding safety, health, and environmental HS. For instance, a very fast pressure transmitter with embedded statistical process monitoring (SPM) can detect pump cavitation to notify operators to check for closed valves, and maintenance to check for plugged strainers. If securely connected across the internet, the corporate global solutions experts are able to compare the problem to other similar plants, the pump manufacturer for product issues, and a service provider to schedule an overhaul. For any business that deals with the production and/or transportation of physical goods, IIOT can create game-changing operational efficiencies and present entirely new business models. The following are examples of ways in which IIOT technology could be applied in diverse industries. Production: this is the industry in which most IIOT technology is currently being implemented. IIOT-enabled machines can self-monitor and predict potential problems, meaning less downtime and greater overall efficiency. Supply chain: with sensor-managed inventory, IIOT technology could take care of ordering supplies just before they go out of stock. This decreases the amount of waste produced while keeping necessary goods in stock and frees up employees to focus on other tasks. Building management: IIOT technology could make building management simpler and more secure. With sensor-driven climate control, the guesswork and frustration involved in manually changing a building's climate will be eliminated. Additionally, devices that monitor entry points in the building and respond to potential threats quickly will increase the building's security. Healthcare: with devices that monitor patients remotely and notify healthcare providers as soon as patient statuses change, IIOT could cause healthcare to become more precise and responsive. Eventually, AI may even be able to take over patients' diagnosis, meaning doctors are able to treat them sooner and more effectively. Retail: IIOT technology has the potential to make quick, intelligent marketing decisions for individual stores, with storefronts that automatically update based on consumer interest and the ability to put together smart promotions. Retail outlets that implement IIOT technology could gain a significant advantage over their competitors. 2.4 Common ground of IoT and IIoT. The similarities of IoT and IIOT both have the same fundamental layer on top of which they are built. With IIOT being a subset of the larger IoT, they automatically share common technologies like sensors, cloud platforms, connectivity, and analytics. Another similarity constitutes the domains for which their application is designed, as well as the standards and regulations they have to conform to in order for them to be successful and commercially available. 2.5 The IoT landscape. Figure 2.1 IoT landscape. Look at the screen. The IoT landscape as shown in the figure 2.1 summarizes the current situation in the IoT world with respect to the standards and the application domains in which these types of products are used. The landscape is valid for both IoT and IIOT products. Both of them are used in various applications which extend from home automation up to farming and agriculture, vertically. On the horizontal, we can find common telecommunication technologies that are used in all the presented application domains. As we can infer from the figure, the application domains are densely populated by several SDOS, standard developing organizations, and industrial or public alliances. 2.6 The IoT Technology Stack. Prior to diving into the details, it is important to understand that not all connected devices are IoT or IoT. In this section, we will understand more about the IoT ecosystem and its fundamental components. The technology basis for any IoT application, whether intended for the consumer or for the industry, is the same and can be abstracted. Therefore, building a product from scratch and calling it an IoT product requires expertise in 6 different domains: device hardware, device software, communications, cloud platform, cloud data, cloud application, device hardware. When we imagine an IoT product, a physical device is automatically brought to mind. This can vary from the extremely simple, say an electronic device sporting some colorful LEDs, to the highly complex, like a device sensing different physical properties and engaging in so-called edge computing. The main requirement when building such products is to incorporate communication technology that allows the device to communicate with other devices or to be connected to the internet. Device software. The software component of any microcontroller-based hardware is called firmware. The firmware is the piece of logic any IoT product needs to operate and perform the desired workload. Communications. The communication is usually realized by connecting to other devices and ultimately to a master gateway, or by connecting directly to the internet using different technologies such as Bluetooth, Wi-Fi, or any other standard communication protocol. Cloud platform. Any IoT product requires a back-end solution where the data is collected, filtered and processed. These are provided by a cloud platform. Cloud data. This component is theoretically optional in an IoT application. Nonetheless, most of the products today incorporate an intelligence for differentiating from other products. Usually, this is perceived as being the most valuable asset of any modern IoT product. Therefore, expertise in areas like machine learning and data science are highly required. Cloud applications. Just as with cloud data, this component is optional, as not all IoT applications offer a GUI-based visualization to the customer. In case this is required, the cloud application must be capable of showing the data collected from the device hardware in the form of a mobile or web application. 2.7 Difference between IoT and IIoT. The Industrial Internet of Things (IoT) is a subcategory of the Internet of Things (IoT), which also includes consumer-facing applications such as wearable devices, smart home technology and self-driving cars. Sensor-embedded devices. Machines and infrastructure that transmit data via the internet and are managed by software are the hallmark of both concepts. IoT is the interconnection of smart devices that monitor, inform, and enhance personal aspects of everyday life via the internet. IoT, in a similar way, builds on the same technology and concepts as IoT to provide the ability to connect businesses, people, machines, data, and devices within an industrial setting specifically targeted to enhance the performance across the manufacturing value chain. While the Industrial Internet of Things falls under the general IoT umbrella, there are a few differences between the two. The key difference is that IoT focuses on connecting machines and devices in industries like manufacturing, healthcare, and logistics, while IoT is generally used to describe consumer-level devices like Fitbits and the whole range of smart home devices from Ring video doorbells to thermostats and refrigerators. Besides the business versus consumer distinction, IoT comes with much higher stakes than IoT due to its massive scale. When a system fails, downtime can result in life-threatening situations or major financial losses. While personal IoT devices do come with privacy concerns and bring up issues about data collection and consent, it's unlikely that failure could result in a true emergency situation. The main differences between the IoT and IoT application domains are highlighted and also shown in the Figure 2.3. Figure 2.3, IIoT and IoT connected through cloud network. Look at the screen. The term IoT, Internet of Things, is often used to refer to ubiquitous, consumer-oriented IoT products. The IoT, on the other hand, stands for Industrial Internet of Things and is a subset of the larger IoT, focusing on the specialized requirements of industrial applications such as manufacturing, oil and gas, and utilities. IoT is a collective term that describes the connection of machines and production plants. The parameters that differentiate the IoT from the industrial IoT include security, interoperability, scalability, precision, programmability, low latency, reliability, resilience, automation, serviceability, security. Any kind of IoT solution requires security, but industrial IoT solutions require more robust measures. Resolving security on a merely superficial level can have a disastrous outcome for a high-volume manufacturing process, resulting in lost production costing huge amounts of money. Another outcome of incorrect action in the control process can put the system into an unstable and unsafe condition. Therefore, IIOT solutions incorporate sophisticated security measures, from secure and resilient system architectures, specialized chipsets, encryption and authentication, threat detection to management processes. On the other side, operation safety is not necessarily an issue in an IoT ecosystem, as these systems do not handle industrial processes. Therefore, no serious safety incident can happen if a wrong decision is made. Interoperability. The IoT interoperability permutations as shown in Figure 2. 4. Figure 2.4, IoT interoperability permutations. Look at the screen. Usually, industrial IoT applications must coexist in environments with significant amounts of legacy operations technologies, OT. These legacy OT don't go away so fast. Therefore, industrial IoT solutions must integrate, support various protocols and data sets, and work reliably with these systems. Scalability. The term industrial suggests large-scale networks supporting a high amount of devices in the order of tens of thousands or more. These devices can be controllers, robots or large machinery, and IoT solutions deployed into these networks must scale seamlessly and support hundreds of thousands of sensors and devices as well as existing non-IoT devices. Precision. Industrial operations require higher levels of accuracy. Automated, high-speed machinery is synchronized to a matter of milliseconds. Therefore, the quality must be assured for such systems. Any small variation in the operation of such high-volume manufacturing processes must be corrected right away. Otherwise, this can result in lost efficiency and downtimes which can affect the revenue considerably. Programmability. The programming and reconfiguration of industrial machines is frequently performed. This can be done remotely, on-site or in the field, and the industrial IoT solutions supporting industrial and manufacturing processes must provide reliable flexibility and adaptability. Low latency. Complementary to precision and accuracy is the requirement for low latency. In industrial applications, anomalies must be quickly detected and corrective actions must be applied in near real time. Reliability. Industrial products are usually designed to operate for 20 to 30 years before a scale replacement is performed. With these strict requirements, like operating in harsh environments, sometimes subject to extreme cold, heat, high vibration, pressure and hazardous conditions, the IIOT applications must assure reliable operability and high availability. A wrong action can put people's lives at risk. The reliability aspect is part of the SRP triad: safety, reliability and productivity. Resilience. The resilience model in 4 acts is shown in the Figure 2.6. Look at the SCREEN. Figure 2.6, Resilience Model. Breakdowns in one part of the system are not unusual in such highly scaled industrial applications. Therefore, the applications must be designed with resilience in mind. To compensate for such faults in the system, the IoT system architectures must be designed to always satisfactorily complete their processes and operations. Automation. The evolution of convergence process of IT and automation is shown in the Figure 2.8. Figure 2.8, Convergence of IT and Automation. Look at the screen. Most of the industrial applications are highly automated from the bottom to top, with limited or absolutely no human intervention. Such IoT solutions are required to support a range of autonomous actions. In order to ensure this, applications do incorporate intelligence into the edge devices, or deep learning capabilities in the system design. Serviceability. IoT solutions operating in industrial environments must be serviceable in order to sustain the levels of performance required. This can extend from swapping out sensors and updating firmware to configuring gateways and servers, the ability to maintain industrial IoT solutions over their entire life cycle is an essential requirement. While building industrial IoT products, one has to focus on the real needs and values of a properly designed cloud data-based architecture with a special focus on the safety, reliability and productivity aspects. The difference between IIoT and IoT is shown in Table 2.1. Table 2.1, the difference between IIoT and IoT. Look at the screen. 2.8 IIoT technologies and concepts. Yet technology can be applied to solve difficult logistic, manufacturing, and supply chain issues that benefit both the manufacturer and consumer. Leveraging IIoT in an existing enterprise is a mutually beneficial aspect of IIoT implementation and can reduce operational costs while ensuring the highest quality possible in a wide variety of an industry's processes. The following are a few examples of current and upcoming technology concepts. Digital twins, the practice of creating a computer model of an object such as a machine or a human organ or a process like weather. By studying the behavior of the twin, it is possible to understand and predict the behavior of the real-world counterpart and address problems before they occur. Electronic logging device, ELD, onboard sensors that monitor speed, driving time and how often individual drivers use their brakes, helping to conserve fuel, improve driver safety and reduce idle resources. If the driver makes a dangerous maneuver or is at the wheel for too long, the driver is alerted and the dispatcher is notified. This technology can replace the paper logs that drivers were once required to fill out every day. Intelligent edge, the place at which data is generated, analyzed, interpreted and addressed. Using the intelligent edge means analysis can be conducted more quickly and the likelihood that the data will be intercepted or otherwise breached is significantly decreased. Predictive maintenance, a system that involves a machine or component with sensors that collect and transmit data and then analyze that data and store it in a database. This database then provides points of comparison for events as they occur. The system eliminates unnecessary maintenance and increases the likelihood of avoiding failure. Radio frequency identification, RFID, a system involves tags and readers, like a smarter version of barcode technology. Readers identify RFID tags using radio waves, meaning the tags can be read by multiple readers at once and over a longer distance than traditional UPCs. RFID tags make it possible to easily track and monitor the things on which they are attached. 2.9 Physical design, IIoT. There are 4 parts to applying IIoT technology to industry. Before a process, plant, system, or enterprise can qualify to be part of the industrial Internet of Things, IIoT, it must fit into 4 categories. Interconnection. The first category is interconnection. There must be interconnection between sensors, algorithms and the operators themselves. This means there must be a human-machine interface, HMI, or a supervisory control and data acquisition, SCADA, system in place that monitors and allows the operators to interact with the process or equipment. This interaction can range from simple monitoring and recording values to complete control and decision-making for RTHE process. Normalization. The second category is the normalization of data, meaning the reorganization of data into something that models the process from where the data is being acquired. For example, monitoring a trend on an HMI to understand the performance of a system over time. This data could even be coming raw from the sensor, algorithm directly to the operator. Data analysis. The analysis of data is the third category. The systems must be able to assist in decision-making and keep the operators safe from tasks that may not be safe. The industries that require automation, smart factories can be dangerous and require extreme safety. The introduction of an automated process, controlled remotely, can increase the safety of the operators and remove them from a dangerous position. Systems automation. Lastly, the systems must become self-reliant over time. This will come from their data acquisitions and established protocols so that the operation can work smarter. A more reliable and automated system makes for a more productive process. 2.10. Industry 4.0, Automation of Industries. Industrial Internet of Things, IIoT, Industry 4.0 and Smart Manufacturing is as shown in Figure 2. 10. All refer to using digital solutions such as automation and big data in physical production and operation spaces. Over the last 400 years, the manufacturing industry has gone through a few key overhauls. The first, second and third industrial revolutions brought changes like steam, electricity and assembly lines, and even computers. We're now in the fourth wave, hence 4.0, and this transformation is all about harnessing the power of real-time, interconnected data and robots and lots of robots. The world is changing all the time. That's just a fact. While adopting new technology can be overwhelming, the benefits are real and exponential. IIOT empowers us to collaborate better, create time and cost efficiencies, automate repetitive tasks, optimize our supply chain, attract younger talent, improve safety, and all of these. Essentially, you can understand your operation better, so that we can make decisions using all of the information available all in real time, of course. In order to understand the IIOT ecosystem, it is pertinent to understand the critical components of IIOT as explained below. Artificial intelligence, AI. Artificial intelligence, AI, is a broad concept where machines carry out tasks in a way that we would consider smart, such as identifying and predicting faults, typically with the ability to learn more behaviors the more you use it. Common examples in business include speech recognition, autonomous machinery, digital assistants. Machine learning is a specific type of AI that requires less human involvement. Machine learning. Machine learning is a specific application of AI based on the idea that we should just be able to give machines access to data and let them learn for themselves, aka, subtract the human component. In the field of machine learning, there are two main types of tasks. Supervised learning. This is done using a ground truth, meaning you have prior knowledge of what the output values should be. Therefore, the goal of supervised learning, given a sample of data and desired outputs, is to best approximate the relationship between the input and output observable in the data. Unsupervised learning. This type of machine learning does not have labeled outputs, so its goal is to infer the natural structure present within a set of data points. Automation. Automation simply means enabling technology, robots, software, etc., to perform the repetitive tasks that your people are spending time on. Automation can improve productivity, accuracy, safety, and more. Business intelligence. Big data isn't that helpful if you don't have a way to use it. Business intelligence offers a system that allows you to quickly access and understand data so that you can use it to make business decisions. It typically requires a data warehouse, analytics engine, and other tools. Cloud computing. With all that awesome data, you need somewhere to put it, right? Cloud computing simply refers to storing your data on a network of remote servers hosted on the internet rather on your hard drive. It allows you access to these resources from any location. Cyber Physical System, CPS. A CPS is a manufacturing operation that's equipped to collect, analyze, use and share real-time data across all areas of the business. It's similar to the ecosystem, see below. Ecosystem. You already know this term from elementary school biology. It's not that different when applied to smart manufacturing. An ecosystem is an operation where different software systems are connected, such as inventory, maintenance, financials, customer relationship management, CRM, and more. Enterprise Asset Management, EAM. An EAM is a platform that allows you to collect, analyze and use asset data to extend equipment life. It aggregates condition data to help you better plan maintenance tasks and priorities. M2M. This is an abbreviation for machine to machine. It's the term for when your equipment has the ability to talk to other equipment, often via IoT sensors, although this communication can be wired or wireless. Predictive analytics. Predictive analytics is an advanced analytics model that uses current and historical data to make predictions about future events. By finding patterns in your data, predictive analytics can help with risk assessment, inventory management, forecasting, and more. System integration. System integration is the process of connecting your different software subsystems, think work order systems, inventory management, accounting, etc., so that they can work together like one unified system. It saves you a ton of time and stress. 2.11 IIoT architecture. A diagrammatic representation of the multi-layered architecture of IIOT is shown in Figure 2. 11. Analytics apps middleware cloud VM backhaul network cybersecurity backbone network gateway, linking device digital sensor network digital sensors. Source. IIOT architecture, standards at every level lets you change wherever by Jonas Burge, https www.linkedin.com/pulse/ear-architecture-standards-every-level-lets-u-change-jonas-burge closing parenthesis EAT spans from instrumentation. Choosing the right technologies for the architecture is critical for the long-term viability of the EAT system. A complex system becomes simpler if it is broken down into modules or layers. The layered approach enables any one layer to be switched as technology evolves, without having to change all the layers in the architecture because standards decouple the layers. For instance, you can change backhaul from cellular, mobile to broadband, change cloud provider, change middleware, change firewall to data diode. And you can mix fieldbus with wireless sensor networks and so on. By building the IIOT architecture on standards, it is possible to switch IIOT-enabled connected services from in-house monitoring to outsourced or vice versa. Things and digital sensors. The things in the Industrial Internet of Things, IoT, are the equipment like compressors, pumps, heat exchangers, cooling towers, blowers, air-cooled heat exchangers, control valves, intelligent on-off valves, relief valve, steam traps, and other equipment found around the plant. Plants already have thousands of sensors connected to the control system, but those are primarily focused on process monitoring and control. Therefore, many additional sensors are required to cover the missing measurements for monitoring the equipment themselves. This equipment needs to be instrumented with sensors to enable them to be monitored remotely, permanent sensing around the clock, for condition monitoring and performance monitoring ensuring plant availability and energy efficiency. These digital sensors include pressure, temperature, level, flow, acoustics, corrosion, vibration, pH, conductivity, position, electric power, H2S gas, and hydrocarbon leakage etc., as shown in the figure 2.13. Look at the screen. Figure 2.13, Things and Digital Sensors. Source: IIOT architecture, standards at every level lets you change wherever by Jonas Burge, https www.linkedin.com/pulse/ear-architecture-standards-every-level-lets-u-change-jonas-burge closing parenthesis. With hundreds or thousands of pieces of equipment in the plant to be monitored. This can translate into many hundreds or thousands of sensors, often referred to as pervasive sensing. Hardwiring each sensor signal point to point would require an inordinate amount of wiring and I/O cards. Therefore, these applications lend themselves very well to digital networking, bus or wireless. Because there will be thousands of these sensors in the plant, it is critical to select high-quality industrial-grade sensors that will last trouble-free and maintenance-free for many years. The sensors touch the equipment and process, it's where cyber meets physical, cyber-physical systems. High-quality industrial-grade sensors will not cost $10 each because they are built to withstand corrosive and abrasive fluids, extremely high pressures and vacuum, high to cryogenic temperatures, vibration, ME, RFI, water and dust ingress, and are suitable for hazardous areas etc. Good sensors are critical to run and maintain the IIOT system itself. An advantage of standards like wireless HART, Foundation Fieldbus, FFHSE, and Modbus etc. is that multiple vendors of gateways support these standards. It is possible to expand the IIOT system with gateways from another vendor without having to make major changes or completely replace the upper layers of the architecture. Backbone network. The backbone network connects the gateways similar to a control system control network. Ethernet and UDP, TCP, iodine monophosphide is used as media and transport for the backbone network. Many industrial Ethernet application protocols exist. To preserve the richness of the sensor data, preserve the application protocol for the backbone networking using the Industrial Ethernet Application Protocol standard corresponding to the Fieldbus protocol standard used for the sensor network. Fieldbus, Profibus DP, Foundation Fieldbus H1, Modbus, RTU, DeviceNet, Wireless HART, Industrial Ethernet, Profinet IO, Foundation Fieldbus HSE, Modbus, TCP, Ethernet, IP, HART IP. Because the backbone network is decoupled from the lower layers, sensors and sensor networks, and upper layers, security, cloud, and apps etc. of the architecture, it is possible to add another backbone network standard in the future should a new more powerful technology become standardized, or even to migrate gateways to other network technologies, without having to make major changes or completely replace the underlying sensors and networks or upper layers of the architecture. Cybersecurity. Cybersecurity is a very important consideration. Multiple options exist to pass data into the cloud to enable enterprise-level or outsourced third-party connected services. The most suitable security solution can be selected depending on the connected service provided and the architecture of the plant automation system. Options include but are not limited to backhaul network, demilitarized zone, DMZ, data diode, physically private network, PPN, Historian cloud connection. The backhaul network connects the plant to the cloud data center, enabling connected services. The media can be the plant's broadband internet connection or a separate mobile, cellular network connection using a mobile, cellular router. IP is used as the transport protocol supporting many application protocols. For a mobile network, cellular network, or satellite network connection where the data charges are high and the bandwidth limited, it may be necessary to use slow polling rates and data caching and report by exception techniques to reduce the data volumes to keep the data charges low. Slower sampling from the applications in the cloud is the easiest way to reduce the data volume because no intermediate protocols or data caching is involved. Hence, no software changes or intermediate drivers have to be used. By using a backhaul network based on IP, it is easy to add new protocols across the same network since IP supports multiple protocols in parallel. It is also possible to change the backhaul network in the future as demands change and new technologies become available. Cloud. The cloud refers to the use of virtual machines, VM, with lots of storage capacity, cloud storage, and computing capacity, cloud computing, running in a remote data center building. The cloud service provider supports with cybersecurity and physical security. If mobile, cellular backhaul is used, it is necessary to make sure the connection between the telecommunication company and the cloud service provider is already established. Middleware, platform. The middleware is usually the historian software which most plants already have at both the plant and enterprise level but could instead be other software, platform, providing the same shared data acquisition, storage, and access security functions. The historian, or other middleware platforms, collects and archives data from the control system and other data sources in the plant over long periods of time in a shared repository, big data. And they enable access to real-time and historical data to analytics and reporting applications. Historians support OPC, Modbus, FFHSE, HART IP, and other standard. Because historians use these standard protocols for data acquisition, it is possible to add new data sources as required in the future. It is even possible to change historian without changing the underlying systems. Analytics apps. Analytics applications receive raw data through the historian, or other middleware platform, from the sensors installed on the equipment and return actionable information as a result of the analysis. There are apps for condition and performance monitoring of equipment as simple as steam traps and relief valves, to more complex equipment like pumps, heat exchangers, cooling towers, compressors, air-cooled heat exchangers, and blowers etc. For instance, a heat exchanger monitoring application receives inlet and outlet temperatures for product and cooling water, steam as well as flow rates and pressure drops from the historian. The analytics app determines the performance and alarms on fouling when it is time to schedule cleaning, displaying this to the user but also returning this information to the historian. The analytics can use historical data or use streaming live data in real time. These apps are what people using the IIOT system actually see. TH apps are the user interface. If equipment performance and condition monitoring is done on-prem, within the plant or at a corporate center of excellence, it is critical these apps are user-friendly, easy to use. If not, the apps, and the entire IIOT system, may fall into disuse. For this reason, the apps are the second most important part after the sensors. As explained for the middleware, the analytics apps are traditionally closely coupled with the historian platform. But this may change in the future. Digital ecosystem. A digital ecosystem means that the components in the system were designed to work well together, often beyond what multiple vendors can achieve through standards because standards have mandatory and optional parts. The beauty of components implemented as a digital ecosystem is that mating components implement the same optional features such that these features can actually be used. A digital ecosystem thus ensures greater functionality. yet still within the framework of the standard. 2.12 What is the Internet of Everything, IOE? The Internet of Everything, IOE, is bringing together people, process, data, and things to make networked connections more relevant and valuable than ever before, turning information into actions that create new capabilities, richer experiences, and unprecedented economic opportunity for businesses, individuals, and countries. Cisco, 2013. In simple terms, IOE is the intelligent connection of people, process, data, and objects have sensors to detect, measure, and assess their status, all connected over public or private networks using standard and proprietary protocols. Pillars of the Internet of Everything, IOE. Proprietary protocols, The following are the 4 pillars of the Internet of Everything: people, connecting people in more relevant, valuable ways. Data, converting data into intelligence to make better decisions. Process, delivering the right information to the right person, or machine, at the right time. Things, physical devices and objects connected to the Internet and each other for intelligent decision making, often called Internet of Things, IoT. The Internet of Things, IoT, is the network of physical objects accessed through the Internet. These objects contain embedded technology to interact with internal states or the external environment. In other words, when objects can sense and communicate, it changes how and where decisions are made, and who makes them. For example, Nest thermostats. 2.13 The difference between IOE and IoT. The Internet of Everything, IOE, with 4 pillars: people, process, data, and things, builds on top of the Internet of Things, IoT, with 1 pillar: things. In addition, IOE further advances the power of the Internet to improve business and industry outcomes, and ultimately make people's lives better by adding to the progress of IoT. Internet of Everything is a new concept as compared to the Internet of Things. Technology experts often state that IOE is the advanced stage of IoT. But it covers the entire area of IoT, even a little wider than IoT. IOE is not merely communication between machines, M2M, but also includes people in it. It makes intuitive interaction between machines and people possible, thus, combining the 2 powerful sources of knowledge and creating a superpower source. In scientific terms, it is put forward as machine to people, M2P, people to machine, P2M, people to people communication, P2P. Therefore, IOE is an intersection where all the roads like people, machines, and technology meet. To make things simpler, IOE is a world of sensors and detectors used to supervise and assess every move of either technology or human and keep in check their status. 2.14 Applications of IOE. Saving lives by connecting roads and hospitals. Traffic crashes influenced the deaths of around 857 bicyclists in 2018 in the US, according to the US Department of Transportation. Some analysts had suggested that these lives could have been saved by leveraging the IOE. Connecting the helmet of a rider to necessary services like traffic signals, hospitals, and nearby police stations through sensors, medical treatment can be provided which can save innumerable lives. This way, information about the patient's criticality can be directly received by the doctor by tracking a hospital around the vicinity right away so that the ambulance reaches the spot on time, enabling the ambulance to interact with the street lights, thus showing green lights all the way, to take the victim to the hospital without any obstacles blocking the way, and allows the doctor to be ready with the essentials by the time patient arrives. Supply chain management. Supply chain management has become a crucial sector after globalization, and there has been immense competition in this sector. If there is a mechanism to alert the trucks about the early harvest, the time of delivery can be arranged with the supermarkets earlier. They can keep in check the available stock so that overstocking sales don't take place. This way the markets can escape from financial losses and the consumers can avail fresh produce every time. Even the harvesters can directly connect with retailers through a common platform and sell their products with profit without having to incur losses bypassing the intermediaries. To further boost customer gratification, customers can interact with the stores through their smartphones and can check notifications on the stock arrivals, and the stores can even give early bird offers. It's a win-win game for all the stakeholders involved. Ever wondered why do you get all the advertisements about items that you just looked for on some app? It's all IOE. It is possible to collect data about the various searches that you look for all day, and IOE helps you by giving all the other available options that may be better. Elderly care. A significant amount of the population is now senior citizenry, and the needs of this section of people are completely different. There have been numerous attempts by various academicians and developers to fulfill these needs and to alleviate their day-to-day hardships. The role of IOE can serve as a solution to these everyday problems by helping the senior citizens stay active and keeping them in touch with their loved ones. There are many robots in the market to nursing the elderly, take care of their health, give them timely medication, and even by conversing with them, these robots can alleviate their mental health issues if any. From assisting them on how to use smartphones to interact with their loved ones to offering companionship to those who are struggling with a disturbed mind. These robots provide emotional simulation, connecting homes for a comfortable life, by establishing connections between different devices and equipment to automating the life processes. IOE has innumerable opportunities to explore. Imagine how you would feel waking up to serene music with hot coffee beside your bed. Imagine a robot feeding and watching your pets timely when you are not home. Imagine a robot that knows your mood, taste, and health status and cooks accordingly. Imagine a home that adjusts to the outside temperature automatically. Doesn't it look like a wonderful and comfortable life? Imagine your home and life becoming like that one from the sci-fi movies you see, like, and desire to have. No, don't imagine it is possible with IOE now. Agriculture is no more a hectic human task. Demand for food supply is ever increasing with increasing population, but the supply, even though increasing, has always remained far below the demand. Governments across the world are bringing in new policies, giving incentives to farmers to equip new technologies, and increasing their spending in the smart city technology as a solution to urban mobility. According to an estimate of the UN, the population living in cities is expected to increase to 68% in 2050 from 55%. With increased growth comes increased challenges. WHO in a report said that approximately 1.35 million people die every year in road accidents. Overcrowding and congestion are two of the major reasons at the heart of this issue. Santa Clara, a city in California, uses cloud-based data to optimize traffic. Highway cameras are centralized in the cloud-based operations center to analyze the videos. More dynamic traffic estimates are provided, hence reducing the congestion on roads and providing the commuters the less congested routes, thereby minimizing the traffic accidents. San Jose, yet another city from Northern California, has piloted a traffic optimization project to understand the peak hour traffics and reduce the accidents thereby caused. These are some cases where IOE has been tried and tested, but there is more to this transformational technology that can serve as examples in the history of technology evolution. IOE in business. The business process has been in existence since the beginning of time and has been growing endlessly. What has caused the growth? The first thing that shaped an impressive business model was the feedback mechanism, thus bringing target marketing in the game, consumer satisfaction being a major factor affecting the entire business. IOE has majorly influenced this department by bringing into market various technologies that identify the needs of its customers. Micromarketing is majorly associated with numerous websites that allow the requirements of the customers to reach the business owners. Not only that, but IOE has also been implemented in the building of ERP software platforms like SAP Cloud Platform. This is used as an extension and integration platform for the running of various applications. SAP Fiori applications support the consumer goods system and enhance the sales process. It is all about reconnecting and re-engaging various service lines to remodel the business. Pros. In this section, let us have a look at some benefits of the Internet of Everything. Information access. Information accessibility will now become a hassle-free task despite your location. The network of devices makes it easy for you to access information from any corner of the earth. Communication. Better communication with interconnected devices with reduced inefficiencies. Affordability. The same data that once took hours to transfer will now be done within no time, hence negligibly reducing the delay and hence reducing the costs involved. Automation. Automation has become the buzzword and has been intriguing humankind for quite a long time. This helps reduce human intervention and boosts the quality of services. Cons. In this section, let us have a look at all the cons of the Internet of Everything. Privacy and security. There are a lot of what ifs and buts in the case of security and privacy. The leakage of data has always been a matter of concern. The privilege of technology comes at the cost of security. This is a major drawback but can be overcome with adequate measures and safety protocols. Data breaching and issues in law enforcement regarding the deep web have blown out in the world recently. Testimony has been held against Facebook accused of leakage of data. Dependability technology has made us depend on it even for small tasks, making humans lazy and killing creativity in humans. The impact of technology is paramount in our everyday life processes. There are other obstacles like the availability of finance for the purpose and availability of power the entire time. The future work. The opportunities available for the future of IOE are endless. The capacity to automate, deploy and secure devices can change the face of industrial processes. The potential is not just in connecting devices and hence in simplifying the life processes but to leverage data that can diversify the business processes, and to overcome these challenges, new service providers come up in the markets, opening new streams of revenue. High stakes have been put by scientists and academicians into IOE, believing it will meet the high-end requirements of the market in the coming future. A human-machine interacting ecosystem is going to provide new experiences to the technology-driven world. New opportunities within remote learning. Developments in wireless networking like Li-Fi, 5G provide further impetus to IOE. Even though it may feel like IOE has covered as much ground as it can, IOE has been mapping new territories, enhancing its implementations and expanding unexpectedly. Signaling more connectivity from cars, electronic gadgets, and toys to traffic lights and home security systems, IOE facilitates connectivity between a range of internet-supported physical devices and non-internet supportive devices. With this emerging involvement of IOE in almost every field, many other technologies can be expected to naturally wane out of the process. Beyond just pure technological concepts for academicians, IOE is capable of transforming the socio-cultural fabric of the world by connecting people and processes. This time is not yet ripe to predict if IOE is the next big bloom, but the statistics, according to market research engine predictions, IOE market is expected to reach $39 trillion by 2024 and grow at 15% CAGR. As well as the dependence on technology life suggests so. 2.15 The future? The Internet of Everything will reinvent industries at three levels: business process, business model, and business moment. At the first level, digital technology is improving our products, services and processes, our customer and constituent experiences, and the way we work in our organizations and within our partnerships, said Hung-Le Hong, Research Vice President and Gartner Fellow. We do what we normally do. But digitalization allows us to do it better or develop better products within our industry. As companies digitalize products and process, completely new ways of doing business in industries emerge. Gartner analysts expect more transformational changes as digitalization reinvents industries at the business model level. Mr. Le Hong gave the examples of Nike, playing on the edge of the healthcare industry with its connected sporting clothes and gear, and Google having a visible presence in autonomous vehicles. These organizations had no business in your industry, and are now reinventing them, said Mr. Le Hong. The third level of digital reinvention is created by the need to compete with unprecedented business velocity and agility. Gartner calls this the business moment. The Internet of Everything will create tens of millions of new objects and sensors, all generating real-time data. Data is money, said Nick Jones, Research Vice President and Distinguished Analyst at Gartner. Businesses will need big data and storage technologies to collect, analyze and store the sheer volume of information. Furthermore, to turn data into money, business and IT leaders will need decisions. As they won't have the time or the capacity to make all the decisions themselves, they will need processing power. Now that digital is embedded in everything we do, every business needs its own flavor of digital strategy. Vanilla is off the menu, said Dave Aaron, Research Vice President and Gartner Fellow. Digital is not an option, not an add-on, and not an afterthought. It is the new reality that requires a comprehensive digital leadership. Gartner predicts that enterprises will make extensive use of IoE technology, and there will be a wide range of products sold into various markets. These will include advanced medical devices, factory automation sensors and applications in industrial robotics, sensor modes for increased agricultural yield, and automotive sensors and infrastructure integrity monitoring systems for diverse areas such as road and railway transportation, water distribution and electrical transmission, an endless list of products and services. But as devices get more connected and collect more data, privacy and security concerns will increase too. How companies decide to balance customer privacy with this wealth of IoE data will be critical. Well, the difference is the intelligent connection. IoT is mostly about physical devices and objects communicating with each other, but IoE brings with it the network intelligence to bind all these concepts together into a cohesive system. IoT has been limited to only machines, thus achieving machine-to-machine communication, but IoE brings together people, processes, data, and things and adds them into the network, therefore not just phone, tablets and PCs but people. Health fitness bands, coffee pots, marine containers all become a node in an intelligent network communicating with each other. The more expansive IoE concepts include, besides M2M communication, M2P, and technology-assisted P2P communication, profoundly affect four major aspects of our lives. The IoE economy will profoundly affect four major aspects of our lives. People. People will be connected to the internet in more relevant ways and will be generating data and interacting with devices not only through mobiles, tablets, PCs and social networks but also through sensors placed on human skins or sewn into clothing, which will provide a person's vital signs. In this way, people will themselves become nodes on the internet. A good example is Nike's wearable fitness bands, which read a person's vital signs, and sports apparel and gears embedded with chips that track the performance of athletes. Things and physical items such as sensors, industry devices, consumer products, enterprise assets will be connected to the internet or to each other, also fetching information from its surroundings, will be more context-aware, more cognitive, more intelligent, often so-called the Internet of Things. As of 1984, only 1,000 devices were connected to the Internet, which increased to about 1 million in 1992 and shot across 10 billion in 2010, and as there is around 50 billion devices connected to the Internet by 2020. These devices fetches data from their environment internally or externally and sends it back to the server for analyzing and making much more intelligent decisions. Data. Rather than simply collecting raw data, these connected devices will be sending higher level, more processed data back to respective servers for faster evaluation or more intelligent decision making. Here the data is more about insightful information and action plan than just a random chunk. Figuring out a way to decipher the right flow of information is the key to making the best use of big data, and as the types of data and sources increase, in order to draw useful insights, there will be a need to classify information and analyze it. Process. With the equivalent to the IOE process, the right information will be delivered to the right person at the right time in an appropriate way. Technology-based businesses will be relying on data to make further decisions and advance their workflow processes and strategies, and will be therefore competing to leverage the data faster than their competitors for agile and faster decision-making. General Electric predicts that IOE can add $15 trillion to the global domestic product, while Cisco estimates $19 trillion in savings and profits for companies that can leverage IOE. But as the number of devices connected to the internet increase and therefore collect more data, privacy is put at risk, which increases security concerns. But as these devices grow more intelligent, hopes is that the device and network will grow knowledgeable enough to detect, stop and prevent any harmful threats. IOE is here and is inevitable. We should embrace ourselves to adapt our lives to the changes that it brings with it. 2.16 Summary. In this unit, we have discussed IIOT, Industry 4.0, Smart Manufacturing, IOE and their applications. Actually, IIOT is nothing but Industrial Internet of Things or Smart Manufacturing. The differences between IIOT and IoT, IIOT and IOE etc. have been clearly described in this unit. Thank you for watching. We will see you in the next video with the next chapter.